Well, I'm gonna be explaining a couple of articles that are very important in continual learning, and because they are very much related to how our brain works. Of course, I'm very ignorant if I say that we know how to model the relationship between hippocampus and thalamus and prefrontal cortex and neocortex, cortical areas. The interaction is very complicated. Even inside the hippocampus, there is a world. And so continual learning is that if we are going from task 1 to task 2, but we don't want to forget what we have learned in task 1. Or if we are in task N, we don't want to forget if we check our task 1 and 2, we still want to have low loss. There are many methods for continual learning. For example, rehearsal. For example, fixed network and dynamic architectures. There is an article by DeepMind here. And there are many paradigms for example, if you just memorize a lot of tasks, then it is not good because you don't have infinite memory, so it's not a natural paradigm. Some of these paradigms are not natural. They are not implemented in our brains. So you can say some of them are generative replay paradigm, some of them are regularization. For example, next lecture I will talk about regularization using that elastic weight consolidation. And this is your hippocampus. This part is your hippocampus and entorhinal cortex, and we have thalamus here, and all of them have interactions with each other, which is very interesting. Otherwise, we cannot save and store very complicated ideas, and episodic memory cannot work well. So this is neural circuits for episodic memory. So inside your hippocampus, there is a world out there. Some of them are doing like a pipeline that first you do, for example, you do pattern separation, and then you do something, and there is a pipeline. It's very complicated. Most of the things that you see on the internet is about cognitive mapping theory, how a mouse, for example, can see those place cells and those things, but it's just a tiny task of hippocampus. Hippocampus does many things that you can write lots of books about hippocampus, because it is like a CTO of a company. It guides everything, and it is a CTO, but the company is still flat. I mean, there is no hierarchy. Everybody loves each other, and so there is a flat hierarchy, although hippocampus is essential. But you see, all of these parts should cooperate with each other, otherwise nothing can happen. And there are many articles about continual learning. For example, I will explain this article in one of my lectures, but the one that I want to explain today is this great article in 2022, Continual Learning Fast and Slow. According to complementary learning systems in neuroscience, humans do effective continual learning through two complementary systems. A fast learning system, which is hippocampus, is well known for indexing. It indexes what is coming from prefrontal, which is your working memory, and hippocampus, it indexes that so that you can store it on your neocortex. So centered on hippocampus for rapid learning of specifics, individual experiences. For example, it doesn't store all of details of experiences. It just tries to see what are the indexes. For example, after we sleep, the consolidation process is done in your brain, and the next day you get up That's why I like mornings very much, because the consolidation process inside my brain is completed and I can learn new things without forgetting what I've learned before. And if you don't sleep, you cannot learn. So continual learning and neuroscience. There are many interesting articles that I will explain later, but if you go there from fast learning to neocortex, this direction is consolidation. But in the next lecture, I will tell you that, even in this lecture, I will tell you that there is another direction as well. From even your neocortex can be used for hippocampus, for episodic, for better indexing. And don't forget, both of them are long-term memory. Many people say that hippocampus is for short-term memory, but no. Your prefrontal cortex is the things that store that is working on working memory. What is in your consciousness, whatever in your consciousness is like the light. When it is turned off, then you don't have any working memory because you are sleeping. So at sleeping, your prefrontal cortex almost, all the neurons activity almost they die, and the process starts from working from neocortex and hippocampus. Their cooperation and their collaboration works when you are sleeping. The idea is that, motivated by these three dual networks. Slow networks. Slow networks is your slow networks is your neocortex, and fast network is your fast network is your hippocampus, and slow network is your neocortex. And so your dual net, and for the fast network, we use supervised loss. But for the slow learner, we use semi-supervised learning. As I said, this direction is called consolidation, but this paper says that there is another direction as well, which is called feature adaptation. Because your fast learner, your hippocampus, uses the things that have been stored inside your neocortex and uses those patterns and retrieves them in order to know how to index the next new episodic memory. And this is called feature adaptation. And the fast learner focuses on supervised learning, while the slow learner focuses on accumulating better representation. As a result, the fast learner can take advantage of the slow representation to learn new tasks more efficiently while retaining the old task knowledge. Two complementary and parallel training processes, dual nets. The representation learning phase involves only the slow network, which continuously optimizes a self-supervised learning loss to model the generic task-agnostic features. Separating the slow learning phase allows dual nets continuously improve representation even when there are no labeled samples. The supervised learning phase involves both learners. So it needs both hippocampus and neocortex, although it is inside your hippocampus. The goal is to train the fast learner a more lightweight model that we can do to supervise learning more efficiently on data streams. And data streams, your visual, auditory cortex, visual cortex, and different source of inputs that you are getting. It's multimodal. It's not just text. It's speech, sound, vision, everything. We also propose a simple feature adaptation mechanism so that the fast learner can incorporate the slow representations into its predictions to ensure good results. And dual nets is just a better version of that. So it prevents the fast learner from co-adapting from the slow features. So it just inserts a dropout layer between the fast learner and slow learners' interactions. It is robust, this new version of dualnet is robust to negative knowledge transfer under the presence of unrelated or interference tasks without the need for modularized representations. So these are notations. We have some data, and so here the slow learner loves redundancy reduction. And Barlow was one of those neuroscientists that he was working on vision and noticed that it uses redundancy reduction. I mean, the correlations between different mass of neurons, we call them mass of neurons, different regions of neurons, let's say groups, or in some articles they call it assembly. It uses the twin. If you read this great article, you will understand that the Barlow algorithm is like this. First, you have, for example, two different perspective of an image. For example, one distorted image, another one, and then you encode both of them. But here you calculate the empirical cross correlation. You want to reduce redundancy. You don't want to represent in different ways. So this is the loss. That this term is just for consistency, but this term is very important. It tries to reduce this cross-correlation. So we call it Barlow twins, BT. And in online continual learning, which is more in harmony with the brain, we use these tasks. We use these updates. So the fast learner, for the fast learner, first, we do this. This is element-wise multiplication. So we have adapted features. These are your adapted features. And then you do this element-wise multiplication. So you have better features, these transform features. And here you have, this is the fast learner's objective. That you have the cross entropy. This is cross entropy between, and pi is always pi here are softmax. First, you should know that the KL divergence between this one and this one should be reduced, because it's like task K compared to different tasks. We want the KL divergence to be reduced, and this is the fast learner's prediction at the end of task I. And this is how fast learner objective is done. And dualnet is, as I said, it's just a variation of that. So here that is that element-wise multiplication to create better features, because not only fast learner features are important, but also you want to augment or you combine with the slow features as well in different layers. So we do it several times, but at the end of the day, this is your fully connected layer that creates the final prediction. And so it's everything is here that you do here. You do train the slow learner using this look-ahead procedure that is here. In look-ahead procedure, you do Barlow twins. You reduce this Barlow twins using that online learning that I showed you. And after that, you should do stochastic gradient descent for a slow learner. And after that, stochastic gradient descent for the fast learner. So phi is the parameters for the slow learner, which is your neocortex. Theta is the parameters for your fast learner, which is hippocampus. And so phi and theta are updated. But you see that this L of TR that I showed you, it needs both the informations from hippocampus and neocortex. So they are working in a cooperative way. And so L loss of TR is here. That you see that it is the KL divergence between the softmax of yi hat and softmax of yk hat. And also the cross entropy between the dual net and your incoming label, because the labels are coming, the new task is coming, because in your episodic memory, it comes from prefrontal cortex to the hippocampus, but hippocampus is also interacting with cortical areas. The cortical areas are responsible for, because it's a huge area in comparison to small area of hippocampus. So hippocampus is here, hippocampus. Prefrontal cortex is here. So prefrontal cortex is what I call working memory, and hippocampus tries to index how should it store everything in this huge neocortex area and all cortical areas. Of course, this is part of that, and hippocampus tries to know how should it index into these different regions of the brain, of the neocortex. And the way that is going to do that is you are minimizing these losses. One of them is supervised learning, the other one is unsupervised learning, or let's say self-supervised. So unsupervised learning is just another term for self-supervised learning. So you see, your image, it could be anything, image, text, or anything. In your fast learning is always convolutional layers. So your fast learner, that hippocampus, uses, for example, convolutional layers. And this neocortex uses residual blocks, residual block 1, residual block 4, because it's very huge. And so hippocampus tries to index those big regions in order to retrieve better, in order to trigger different episodes. For example, this is your hippocampus and this is your neocortex. For example, this is index, it triggers a big area. So there are lots of recurrent neural networks here, lots of recurrent neural networks here, and they are interacting with each other, but each one has an index. For example, index 1, index 2, index 48, and it just knows that, for example, index 48 is this region inside hippocampus is related to this region in your neocortex. And this region, so the weights between them it's like the plasticity is increased because it wants to associating this index into these regions. So details are here in your neocortex, but just a cue or a very simple sign is in hippocampus. So it's just indexing I and I is 1, 2, and it is related, so the details are in neocortex. But here is prefrontal cortex, PF. A working memory during the day, you're thinking about different things. It is just a stream, because all of the auditory and visual data, auditory cortex, visual cortex, all of them come to the cortex, and then during the day, so you have your prefrontal cortex is doing working memory, but this is the hippocampus that knows how to use these valuable information in order to store it in different parts of neocortex, because this is the process of learning. Otherwise, we don't learn. If we don't have hippocampus, everything is gone. So this link is gone. So you don't learn. You can just work on your previous ideas and previous things that you have learned, and you cannot learn any new thing. For example, when we are sleeping, this is cut. You are not learning new things. You don't have working memory. Your consciousness is off. And whatever you're doing is just the consolidation process, going from hippocampus to your neocortex. And of course, the opposite one is adaptation, which is discussed in this paper. So also neocortex is useful because it shows how hippocampus can can do better indexing. And so this is very important. And this article that uses Barlow twins